we're going to talk about some of the fundamental results that follow immediately from the definition of probability. So first, for any measurable set, the probability of A complement is equal to 1 minus the probability of A. And to do this, we're just going to use rules from set theory and the definition of probability. So A intersect A complement is the empty set for any set A, because there's never a point in a set and its complement. So by the definition of probability, the probability of A union A complement equals the probability of A plus the probability of A complement. Remember that for a union, if the sets are disjoint, it becomes a sum of the probabilities. And let omega represent the universal set. So by definition, the probability of omega equals 1. Using those two rules combined, we get the probability of A plus the probability of A complement is equal to the probability of A union A complement, which is the probability of omega, which equals 1. So 1 is equal to this value here. And now, taking these two things as being equal, we can subtract the probability of A over to the other side. So the probability of A complement equals 1 minus the probability of A. As a corollary to this, or just a result that immediately follows, the probability of the empty set equals 0. And that's because the empty set is the complement of the universal set, or the sample space in this case. So the probability of the empty set is the probability of the sample space complement, or 1 minus the probability of the sample space, which is 1 minus 1, or in other words, 0. Probabilities always satisfy the inclusion-exclusion principle. So for any two sets A and B, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So to show this, we're going to first break up the set A union B into A and B intersect A complement. So every element in A union B is either an element of A or it's not an element of A, meaning that it's in B. And since it's in B and not in A, that means it's in B and it's in A complement. So everything in A union B is either in A or in B intersect A complement. You can formally show this using the distributive property in sets. So A union B intersect A complement is equal to A union B intersect A union A complement, which is A union B intersect omega, and anything intersect the entire set is just it's just itself, in this case A union B. Also, A intersect B intersect A complement is empty, and that's because A intersect A complement is empty. And then anything intersected with the empty set is also empty. So, the probability of A union B, which is the probability of A union B intersect A complement, is the probability of A plus the probability of B intersect A complement. And to this, we're going to add the probability of A intersect B minus the probability of A intersect B, which in other words is just adding 0, because those two terms cancel. It's just a fancy manipulation so that we can get the formula we want. And this would say the probability of A plus the probability of B intersect A complement is the probability of A plus the probability of B intersect A complement plus P of A intersects B minus P of A intersects B. Keeping in mind that these two things really just cancel. So it's just saying it's equal to itself. But if we look at these middle two sets, what happens here is their intersection is empty, because the first set is everything in B that's in A complement, and the second one is everything that's in B that's also in A. And so therefore we can put them together, and this becomes the probability of B intersect A complement union B intersect A. And since those are all the elements that are in B and not in A, with the elements that are in B and in A, that's just B itself, because everything in B is either in A or it's not in A. Which gives us that this probability is equal to P of A plus B of B minus P of A intersect B. And the term that we started with way at the top was P of A union B, whenever we started doing this computation. So this shows that P of A union B is equal to P of A plus P of B minus P of A intersects B. And another corollary we get from that is the probability of A intersect B is equal to the probability of A plus the probability of B minus probability of A union B. And that's just by adding this over to both sides and then subtracting this one over. So we get this being positive and this being negative. Next is an order relationship. So if A is a subset of B, then the probability of A is less than or equal to the probability of B. So if we apply distribution twice, you can show that, which we used above, that B is equal to B intersect A union B intersect A complement. So everything in B is either in A or it isn't. And if A is a subset of B, then A intersect B is just A itself, because everything that's in A and B just has to be in A. There's nothing that's in B that's out. There's nothing in A that's outside of B. So B in this case would equal A union A complement intersect B. And these two sets are disjoint. So the probability of B is equal to the probability of A plus the probability of A complement intersect B. But by definition, the probability of any set is bigger than or equal to 0. So the probability of B is equal to the probability of A plus something bigger than or equal to 0, which means that the probability of B has got to be bigger than or equal to the probability of A. And finally, for set differences, if B is a subset of A, then the probability of A minus B is the probability of A minus the probability of B. So once again, we're going to use this trick that a set A can be written as everything in A that's in B unioned with everything in A that's not in B. And since B is a subset of A intersect B equals B. So using the fact that these are disjoint events, we get the probability of A is equal to the probability of A intersects B plus the probability of A intersects B complement. And using the fact that A intersects B just equals B, this is equal to the probability of B plus the probability of B or A intersects B complement. So by definition of set subtraction, A intersects B complement just is B, A minus B. So that's the definition. And subtracting this B to the other side in this equation, so I'm going to take this B, well, here when I say subtracting it over, I mean that this is equal to this. So the probability of A equals the probability of B plus the probability of A intersects B complement. And we're going to take this probability of B over. So this is the probability of A minus the probability of B equals the probability of A minus B. And that's what we wanted to show.